Hi guys, this is Mrs. Villette, and I'm going to remind you of what we've learned so far about sinusoidal functions. Sinusoidal functions are of the form y equals a sine omega x plus k, or y equals a cosine omega x plus k. It's very important that before you start, you understand what the parent functions, so just a regular sine or a regular cosine graph, look like. So the a, omega, and the k, those each do something different to the function. They relate to, in order, the amplitude, period, and midline. But before I discuss what each one of these does, we're just going to define generally what amplitude, midline, and period are. So the amplitude is defined to be the half of the distance between the maximum and the minimum. So if I do the maximum value, subtract the minimum value, and divide it by 2, that is going to be the amplitude. And in this case, for a trigonometric function, we're going to say that the amplitude is the absolute value of the A. The period is the distance from trough to trough or crest to crest. So it's the distance from crest to crest. We can also look at this a little bit differently when we're talking about a sine function, and I'll talk about this in the red graph over here. But the formula we're going to use for the period is t equals 2 pi over omega, and oftentimes we'll reorganize this formula to say omega is 2 pi over the period. And then the midline, just generally, is the average of the maximum and the minimum. So it's right between the maximum and the minimum. So it's the max plus min divided by 2, or the formula for it relates to the k value. So it's the y equals k. So let's take a look at these two functions that I have over here and see if we can identify the amplitude, the period, and the midline. So in the first function, for the amplitude, what I'm looking for is I'm trying to find half of the distance between the maximum and the minimum. So if I look at this graph, I can figure out that the distance between the maximum and minimum is 4, that looks like. So my amplitude, or my absolute value of A, is half of 4, which is 2. Now my period is measured from crest to crest. So I could take this crest over here and that crest right there and measure how long it takes to do that. So we have to actually figure out where those are. Looking at my tick marks, I know that this is negative pi over 2 over here. So half of that is pi over 4. This must be negative pi over 8. And then halfway between 0 and pi over 2 is pi over 4. Pi over 8 more than that is 3 pi over 8. So the distance between those is actually 4 pi over 8. So my period is 4 pi over 8, or pi over 2. There would have actually been an easier way to see this, and that would have been to just look at what one period of a sine function looks like. A sine function starts at its midline, and this is actually an inverted or reversed over the axis sign, but it goes to, in this case, minimum, midline, maximum, and then midline again, and I can quite clearly see that that distance is pi over 2. However you do it, you're going to get the same answer. And then the last thing is the midline. So the midline is this line that slits the function right down the middle horizontally. And so that midline is y equals 1. That's your k value. We could actually put all of this together to figure out that the equation for this is actually y equals, it's going to be negative 2 sine, I need to know what the omega is, so it's going to be omega x plus 1. If I want to figure out what the omega is, that's where we're going to use omega is 2 pi over the period. So my omega is 2 pi divided by pi over 2. And if I invert and multiply, I get 4. So then my function is y equals -2 sine of 4x plus 1. So why is it -2? It's -2 because normally a sine function would start at its midline and go up, but this function starts at its midline and goes down. So it's been reversed over the midline. So that's why it's a -2. The other thing that you need to know about this omega is the omega tells you how many periods fit into a normal 2 pi. So if I look here, t equals 2 pi over omega, the omega is how many periods fit into 2 pi. Well, since this period is pi over 2, I can tell that 4 full periods are going to fit into 2 pi because pi over 2 is 1/4 of 2 pi. So that's why this omega is 4 here. Okay, I'm going to go through this next example a little more quickly. This example, I can see that the amplitude is 3. So the absolute value of A is 3. It's a distance of 6 between the maximum and minimum. The amplitude is half of that. It looks like the period is 4 pi, and I can see that by going from a trough to a trough, and that's a distance of 4 pi. So the period is 4 pi. We could go ahead and figure out that our omega then is 2 pi over 4 pi, or 1/2. Okay, and then the last thing we need to know is the midline. The midline is that line that splits it horizontally, and since our amplitude is 3, we should just be able to count an amplitude from a maximum or a minimum. So if I start at a minimum and I count 3 units back, that should take me to the midline. So the midline is y equals -2. Now this one looks more like a cosine function to me, and it doesn't look like it's been reflected at all. So it should just be y equals 3 cosine of 1/2 x subtract 2. Okay, that's a little more advanced than what we've done in class so far, but I want to give you a preview of what's going on there. Okay, so now I'm going to go through 2 examples of graphing these sinusoidal functions. So the first one is y equals -2 sine of 3x. So I know that the amplitude is the absolute value of -2, which is just 2. The midline is y equals 0, because there's nothing added or subtracted. And then the period is 2 pi over 3. So the first thing I need to do is decide how to scale my axes. And the thing that we need to remember about a sine function is one period of it looks basically like this. And there are kind of 4 equal pieces. Right in half, right here is where it switches from concave down to concave up, and then halfway between there, it hits its maximum, and halfway between the other half, it hits its minimum. So when I'm thinking about this 2 pi over 3, I actually want to think about splitting that into 4 equal pieces. So I'm thinking 2 pi over 3 divided by 4 or multiplied by 1/4 is 2 pi over 12 or pi over 6. That's a good scaling for your axes. Now I'm actually going to label them just every pi over 3 though, so because I've got grid marks splitting them in half. So pi over 3, 2 pi over 3, 3 pi over 3, or just pi, 4 pi over 3. And we'll do the same kind of deal in the reverse. So negative pi over 3, negative 2 pi over 3, negative pi, and then negative 4 pi over 3. Okay, just for comparison, I'm going to try to graph what a regular sine function looks like compared to this. Let's go ahead and make our y scale 1s. And I'm just going to do it dotted. A regular sine function goes through the point 0, 0, pi 0, and then pi over 2, 1. And then it would also go through negative pi over 2, negative 1, and then negative pi 0. So this is what a regular sine function looks like. We'll just go ahead and connect those. And then it continues like that. So this is the graph of just y equals sine of x. So how does my function compare? Well, its amplitude is twice as big, but it's also reflected over the x-axis. What that means is I'm going to multiply all of the y values by -2. But in addition to this, my period is 2 pi over 3, so I should be fitting my whole entire function in a space of 2 pi over 3. So it's going to start at 0, and it's going to end its period at 2 pi over 3. Remember, normally a sine function, we've got the graph right down here, starts at its midline, goes up to its maximum, back to the midline, down to the minimum, back up to the midline. It hits its midline again halfway through its full period. So it's going to hit its midline again here. Oops, I didn't want to do that. Undo. Okay, there we go. So it hits its midline again right here halfway at pi over 3. But it's going to be flipped upside down compared to a regular sine function with an amplitude of 2. So normally it would hit its minimum halfway between those two midlines, or its maximum there, but now it's going to hit its minimum instead. And then it's going to be reversed. So one period of it looks like this, and then I will just keep on doing that. So it's going to hit its midline basically every pi over 3, and then it's going to hit its maximum and minimums halfway between those. And then it just keeps on going on like that. So you can see that the period is 2 pi over 3. What that really means is that you could fit 3 periods into the normal amount of space that a sine period would take up. So that's what this 3 here means. You can fit 3 periods. So if you were to extend this all the way out to 2 pi, you would have 3 of those full periods there. Now, if you're not comfortable with doing these transformations, you can always make a table of values. And when you make the table of values, you want to pick values of x that turn out kind of nice for this function. So if I put x equals 0, my y is -2 times the sine of 0. Sine of 0 is just 0, so anything multiplied by 0 is 0. Now normally I might put something like, let's say, pi over 2 into this function. If I do that, I get -2 sine of 3 pi over 2. So -2 multiplied by -1, which is 2. Okay, well that matches this point that I have right up here, pi over 2, comma 2, but I've missed all of these other interesting points in between, so I've kind of skipped ahead a little bit. So this 3x actually compresses my function horizontally, so I'm going to try even smaller x values, like pi over 6. Because if I put this into 3x, now I have 3 times pi over 6, so -2 times sine of pi over 2, sine of pi over 2 is 1, and so I get -2. And then I could try something like pi over 3, -2 sine of 3 times pi over 3. Now I'm doing sine of pi. Sine of pi is 0, so this whole thing gets me 0. So this is another way that you can do it. I find it easier personally just to do it based on transformations. So let's do one more problem. This problem has all of the things put together. It has an amplitude change, a period change, and a midline. So y equals 3 cosine 1/3 x plus 2. So what do we need to know? We need to know the amplitude, the midline, and the period. So the amplitude is the absolute value of the A, which is 3. The period is 2 pi over 1/3, which is 6 pi. And then the midline is y equals 2. Okay, a normal cosine graph would start at its maximum of 1. At pi over 2, it's going to be at its midline. Then at pi, it's going to be at its minimum. At 3 pi over 2, it's at midline again. And at 2 pi, it's at its maximum. So we still kind of have this idea of 4 parts of the graph. So we have kind of this part where we go from maximum to midline, midline to minimum, minimum to midline, and then midline to maximum. So that's what a regular cosine graph looks like. Of course, this is 1 and this is -1. So we want to use that idea of what one period of a cosine function looks like. But we want to draw a cosine function that's not reflected about the axis or midline at all, but whose amplitude is 3 times as big, whose period is 6 pi, also 3 times as big, and whose midline is 2. So what I like to do in these cases is go ahead and draw a box. I want 6 pi, and I'm going to count kind of 4 tick marks off and make it 6 pi. Then we have to think about, okay, 6 pi divided by 4 is 3 pi over 2. That's what each quarter, if that's what we're going to call them, of this period looks like. So this is 3 pi over 2, 6 pi over 2, is that what I wanted to say? Yes, 6 pi over 2, which is 3 pi. That should make sense. That's half of the period. Then 9 pi over 2. So I said 3 pi over 2 plus another 3 pi over 2, 6 pi over 2 plus another 3 pi over 2, 9 pi over 2, and then 6 pi. That's where one period of my function is going to fit horizontally. But the midline is at 2. So our midline is going to be right here at y equals 2. My amplitude is to go up 3 units from that and 3 units down. So I actually don't have enough room. I'm going to rework how I'm going to scale things. And we will make this be y equals 2. So then our scale goes 2, 4, 6, etc. So my amplitude needs to go up 3 and down 3. So my maximum is 3 above 2, so my maximum is right here at 5, and then my minimum is right here at -1. So I'm going to box this out. This box is where I should be filling in my one period of a cosine function. It's not a reflected cosine function, it's just a regular cosine function with a little bit of change to the amplitude, the midline, and the period. So I look at my reference over here of what the parent function looks like. It starts at its maximum. Well, the new maximum is right here. And the new minimum is down here at -1. And then we've got our midline here at 2. Okay, so I'm going to start at my maximum. I'm also going to end at my maximum. That's what a cosine period does. Halfway through its period, it should be at its minimum. And then halfway between those, it should be at its midline. So halfway, we already did all the calculations for where those would be. Then I connect those nice and smooth. And then I try to continue that. So 2 grid boxes over, it should be at its midline again. And 2 grid boxes, it should be at its midline. Continuing to the left of this, 2 to the left, it should be at its midline. 2 more to the left, it should be at its minimum. And then its midline again. and then it's maximum, then it's midline again, and then it's minimum. That's as far as I can really go on this graph. Okay, and if you didn't do a very good job, then you just go over it again with thicker pen to try to hide whatever doesn't look so great. So we'll just do even bigger. And there you have it. So you should be able to do your My Math Lab with this video and even more. And I'm sorry it went a little bit long once I get going. I just want to explain everything. We will do a little bit more with this in class this week, but we are also going to move on to one more transformation, which is a horizontal shift.